Aaron Nuba for the EE599 final project submission. Today, I will be presenting my final project, which is a survey on photoelectronic applications for machine learning. To to start out, I want to talk about current computing limitations. Computers excel at solving problems with simple and reliable rules, such as arithmetic operations or processing keystroke inputs. And they're designed to perform these tasks quickly and efficiently without cease to aid in various other tasks. However, tasks that involve complex dependencies and weak rules for those dependencies are difficult to implement, such as decision making or image recognition, and the standard CPU core is in no way optimized for efficient and expedited arithmetic that are demanded from these tasks, because they don't leverage the massive parallelism that these tasks possess. Even graphics processing units, which can handle the parallelism better, are in no way the best solution for these tasks. So to start out, I want to demonstrate these weak rules and dependencies. This is an image of a cat. This is a cat to me and hopefully everyone who is viewing this presentation, but this is a cat. However, if you rotate this image upside down, we still recognize it as a cat. The weak rules and dependencies that are still in place allow us to recognize this as a cat despite it being flipped upside down. Now, furthermore, the same goes for if a portion of this image is obscured. We still recognize it as a cat. So to demonstrate that, I used one specific image to demonstrate this best because I wanted to really hit home to a computer. Those were three separate images. There was the initial image, the upside down image, and then the partially blocked image that's currently on screen. A strict rule set for recognizing one of those would fail to recognize the other two because the rule set would be too strict, it would mislabel it. Furthermore, it doesn't account for other aspects, such as if we add a second cat into the image. Moving on to current computing limitations. Moore's law is breaking down due to electronic limitations such as thermal energy, power consumption, and processing speed. There is another issue that current computers are facing, one that is more physical. Moore's law says that the number of transistors on a chip doubles every decade, and this no longer holds true. For thermal energy, as transistors get smaller, so does their surface area for heat dissipation. This has led to unwanted dark silicon, which is essentially circuitry that cannot be powered on for a given thermal design power constraint. For power consumption, electricity takes power to generate potential voltages and sustain electron flow. This power demand is continuous as these voltages and currents cannot sustain themselves. And one of the biggest power losses in computers is communication. This is communication between memory and the CPU due to the lack of co-location of processing in memory. The energy for communication has to be continuously sustained, which is a recipe for excessive power draw. For processing speed, electricity is limited to the low gigahertz range, which is difficulty keeping up with the ever-increasing processing demand. Previously limited by technology, this was smaller, but as with everything else, it kept increasing, but we are quickly approaching the physical limit of how fast the electrons can propagate to make the voltages and currents that are necessary. These flaws are exacerbated in reference to the aforementioned computing issue. Here is a graph of Moore's law. On the left is the projected, and on the right is it slowly dying out. For example, the clock frequency, it has hit a wall. It can't go past in our case, low gigahertz. It can't go past that, unfortunately. Transistor density, transistor energy efficiency, and system energy. Well, transistor energy and transistor density are unfortunately bottlenecking. And I want to note how the graph's rate of increase is logarithmic, so improvements are orders of magnitude higher. And there's a decrease in the slope for the lines. There's a hard stop for clock frequency, a decrease in transistor energy, and a decrease in transistor density. And system energy is still increasing in orders of magnitude despite these losses. So a potential solution for this is neural networks. Neural networks can solve the soft implementation role. It utilizes neurons with different weights and biases. It computes with matrix multiplication, and utilizing matrix multiplication allows for parallel computation. This significantly enhances efficiency and decreases latency as the wait time for inputs for the next step of computation arrive at similar times. And it can have multiple hidden layers. And hidden layers are neurons that aren't directly tied to the input or the output. Their inclusion can help increase the accuracy of the neural network greatly. However, despite these advances, electronically implemented neural networks still face the same problems of electronic circuits. Training for neural networks is excessively energy intensive on electrical circuits. For example, BERT, a Google language model, required 1,438 pounds of carbon dioxide for training, and a single passenger trip from New York to San Francisco generates a comparable carbon footprint. Here's just a brief diagram of how the neurons would be layered out. Inputs are fed into their respective neurons where a weight and bias are applied that determines the output, which are then the input for the next layer or the output to the system itself. Next are photoelectronics. Photoelectronics can alleviate the issues of electrical circuits as they have very little thermal dissipation, since optoelectronics do not generate heat in the same way that electrical circuits do. Depending on the methods for tuning used, as we'll get into later, little to no heat can be generated. They have very low power consumption, as photons only require energy and generation. If guided through an appropriate medium, they are self-sustaining and travel until external termination, such as being absorbed or being reflected away. And then photonic processing speed. Since photons travel at the speed of light, propagation time is near instantaneous, and as a result, it is unlikely that photons themselves will become a speed bottleneck. Photoelectronics also have the added benefit of analog processing, which can be useful in neural networks. Next is the photonic component overview. Optical convolutional neural networks brings lower training costs, lower computation, and better predictive performance from Few et al., page 3, one of my sources. So first up is the waveguides. Waveguides are compatible with complementary metal oxide semiconductor fabrication methods. These have high refractive indexes, and high refractive indexes allow the waveguides to be smaller, which decreases area consumption and improves area efficiency. Silicon on insulator has the highest refractive index and by extension has the smallest area footprint. Insulators have low refractive indices, and low refractive indices prevent light from the waveguides from leaking into the substrate itself. Next are the microring resonators. These are a key device. Microring resonators are passive devices that can be used for wavelength selectivity and signal modulation. The size of the ring is adjusted for resonance with different wavelengths, and resonance allows the diversion and relocation of different wavelengths. Adiabatic bends can minimize bend losses as they are more smoothly curved compared to their circular counterparts. Next are the Mach-Zehnder interferometers. Mach-Zehnder interferometers can be used as wavelength division multiplexers, optical switches, electro-optical modulators, and Mach-Zehnder interferometers are comprised of two wide junctions and two waveguide arms. One of the wide junctions acts as a beam splitter and the other one acts as a beam coupler. Next are the optical phase shifters. Research is being conducted on alternatives to thermal phase shifting and tunable couplers, as currently, for microring resonators specifically, we use tungsten heaters in order to heat the not exclusive to microring resonators. Many of the phase shift demands in photoelectronics are met through thermal tuning. The problem is that electrical heaters burn power continuously. Furthermore, specifically for waveguides that will be in close proximity to microring resonators, thermal crosstalk will export the unwanted thermal energy to the waveguides. Research is being conducted on alternatives such as carriers. These are diodes and capacitors. They have less of a magnitude of phase shifting and still introduce significant loss. There are liquid crystals which have high efficiency as actuators and phase shifters, but they are difficult to fabricate as it requires depositing liquids during the fabrication process, which is difficult. There are pockels, which are polymers and perovskites, and mechanical systems themselves. However, mechanical movement is difficult as it requires undercutting the waveguide, but it does provide satisfactory results. Next, I want to talk about two kinds of optical neural networks. First is non-integrated optical neural networks. These are mainly based on 4F systems, diffractive elements, and other optical components, and they can achieve large computing capacity. 4F systems are optical transfer systems that consist of two lenses that can achieve a Fourier transform of the input optical field. Fabrication of these non-integrated optical neural networks may cause unavoidable alignment errors, and this error accumulates with an increase in optical neural network layers. The connection of discrete components is both a blessing and a curse in the sense that it aids to achieving large computing capacity at the cost of harming scalability with these alignment errors. And large-scale implementation for non-integrated optical neural networks is tough. As a result of this limitation, overall scalability and universality are significantly diminished, and as such, non-integrated optical neural networks are best suited for specialized applications such as pre-sensing optical calculation. Integrated neural networks, as the alternative, complementary metal oxide semiconductor alleviates the alignment error problem between discrete components. As a result of CMOS alleviating this alignment error, this permits scalability and versatility for integrated optical neural networks. Integrated optical neural networks require constant energy supplies during the working process. As electronic CMOS has a constant power draw to sustain voltages and currents, this limits large-scale expansion in part due to thermal crosstalk, which harms the computing capacity to a level lower than the processor's maximum. And furthermore, despite its promise, it's very difficult to simultaneously achieve all the advantages on the same optical neural network. So next is the research in photonic neural networks. Photonic interconnects are extremely well suited for collective operations that involve data to be broadcast or multicast, since signals can be easily split without need for replication. This feature is eye-catching in convolutional neural networks, as receptive fields of the input volume have shared parameters. Compared to its electronic-based counterpart, this is far more efficient, as broadcasts induce high energy costs in electronic circuits. First is the asymmetric loop-terminating Mach-Zehnder interferometers. Asymmetric loop-terminating Mach-Zehnder interferometers have smaller footprints and boosted performance compared to their continuous counterpart. The loop termination aspect of the Mach-Zehnder interferometer allows incoming light to travel back and forth through the interferometer, which allows the advantages listed, which allows multiple advantages such as higher rate of change. It achieves the free spectral range using half the path length difference, and full width at half max is half compared to their continuous counterparts. The properties listed can also be useful in applications such as modulators and sensors. The transmission spectrum can be tuned using DC coupling coefficients as the relative intensities of the even and odd resonances change. The main bandwidth limitation is the resistor capacitor time constant, and decreasing the capacitance of the modulators will further enhance performance. And the asymmetric Mach-Zehnder interferometer sensor permits the engineering of wavelength sensitivity and figure of merit independently. Next is SCANA, which focused on stochastic computing. Stochastic computing offers advantages over binary computing, such as lower power consumption, small circuit area, low-cost arithmetic operations, and high error tolerance. Fabricated microring resonator optical stochastic multipliers realize improvements in throughput and energy efficiency. It uses a novel photocharge accumulator, and the peripherals of optical stochastic multipliers can incur latency. Next is Pixel, a photonic neural network accelerator. It utilizes optical multiply and accumulate units. Linear transformations can be performed at the speed of light, and matrix operations can be performed without significant power consumption. Optical electrical circuits are capable of reducing the multiply accumulate operation down to a bitwise AND, which is then followed by shift accumulate. And for an all optical multiply accumulate, if we ensure the path length connecting one Mach-Zehnder interferometer's output to the next Mach-Zehnder interferometer's input is equal to the bit transmission period, 2 bits can be combined at the output. Over on the right is the pixel architecture of these optical multiply and accumulate units. Continuing on, optical electrical and optical designs favor more bits per lane. In smaller bits per lane, the hybrid method works best, in part due to the size of the optical component. A higher bits per lane count only amounts in a small jump of energy consumption for all optical devices, thanks to Mach-Zehnder interferometers' efficient accumulation. Energy efficiencies as the number of bits per lane increases. And as the bits per lane increases in electrical devices, the energy consumption increases in a fast exponential fashion, as we'll see on the next slide. The drawback comes when there is a low number of bits per lane or when the number of lanes is low in these scenarios. A potential research area is minimizing the photonic component area. As you can see over on the right, all optical has the highest. All optical has a few orders of magnitude higher than electrical, and hybrid methods still are a few orders of magnitude higher than purely electrical. Furthermore, despite the energy efficiency displayed on the next slide, the device footprint of optical devices is far larger than that of electrical devices. So over here, at 2 bits per lane, all optical architecture consistently beats out all electrical in terms of energy efficiency. The hybrid method is ideal in energy per bit scenarios of 8 lanes or more until including 8 bits per lane. Optical is ideal for lanes less than 8 until non-inclusively 16 bits per lane. Next is the digital electronics and analog photonics convolutional neural networks for deep CNNs. This aims to improve matrix multiplication throughput using photonic neural networks. Upwards of 80% of total processing time in electronic processors is spent on convolution. Weight banks in the system are not modified until a new kernel is applied. Modifying weight banks is very time intensive, and further parallelization is reached through handling the photonic architecture as a convolutional unit with a single output. 6-bit deep CNNs can admit bit-like distortions of 2 bits without performance flaws. Deep CNNs designed with 4 bits or less have significantly diminished performance, and nonlinear transfer functions can suppress noise from analog states. The simulated network achieved an accuracy of 97.6%, which is comparable to the standard deep neural network. However, an unfortunate repercussion of the system is that negative inputs require additional optical or electronic control circuitry. Furthermore, this could result in a loss of precision. The largest bottleneck with the system is the I/O interface through the digital to analog and the analog to digital converters. Next are the photonic tensor cores. Performing multiply accumulate operations in the photonic domain has near zero static power consumption. Multiply accumulate operations in the photonic domain also have low latency, depending on it only depends on the time of flight of the photon. It is considered a full-fledged analog processor when performing inference, as the photonic tensor core does not rely on any logic architecture or transduction from off-chip memory, and it utilizes an integrated optimized photonic memory, and the performance of the weighting function is entirely passive. It utilizes phase change materials. Extracted weights are set through electrothermal switching. Binary weights can preserve overall memory while reducing tungsten heaters. However, this unfortunately requires differing writing and erasing times and voltages. This is a layout of the photonic dot product engine that makes ample use of microring resonators for matrix arithmetic. Next are the photonic accelerators for mixed-size tensors. Current tensor product cores struggle with mixed-size tensors. Mapping mixed-size tensors onto fixed tensor product cores leads to low hardware utilization, which diminishes achievable performance and energy efficiency. Mixed-size tensors were brought about as a method to increase the efficiency of executing convolutional neural networks through reducing computation, memory requirements, and communication. This led to the employment of compressed mixed-size tensors in convolutional neural networks. To solve this, reconfigurable vector dot product elements were designed. Reconfigurable vector dot products are designed to substantially improve multiple areas of hardware utilization, namely determining the reaggregation size based on the smallest decomposed kernel vector. Determining reaggregation size based on the most common smallest decomposed kernel vector maximizes opportunity for utilization efficiency. For processing flexibility, if the employed accelerator hardware supports more parallelism than necessary, it can lead to lower hardware utilization efficiency. And parallelization for tensor processing, determining reaggregation size based on the smallest and most common decomposed kernel vector, again, maximizes the opportunities for processing parallelism. And for energy efficiency, efficient parallelism and hardware utilization increases energy efficiency as the energy drawn in is used more towards the computation instead of through static power consumption. This highlights this work highlights concerns with prior works regarding scalability. It analyzes the scalability of both aggregation modulation and aggregation modulation tensor product core architectures to capture the vector dot product element interdependence. Furthermore, oops. Furthermore, aggregation modulation tensor product cores. It was found that aggregation modulation tensor product cores need more area as their decomposed kernel vectors need to be placed further from their decomposed input vector to avoid thermal crosstalk, which affects achievable vector dot product element size. However, research is currently underway for the current precision limits. It was determined that neither the aggregation modulation nor the modulation aggregation modulation tensor product core architectures should be used to achieve precision higher than 4 bits based on the technology that is currently available. Next again are photonic tensor cores from a different source. For this source, they explored dissipative Kerr solutions, which encoded image data onto individual comb teeth and fixed convolution kernels in a non-volatile configuration. These enhancements were made to reduce the footprint cost of the photonic components, and this was achievable through multiplexing computations in the same photonic core. It encodes multiple input vectors onto multiple lines of a coherent chip scale frequency comb. This is done to remove sequential operations and duplicated physical hardware, and it is limited only by the speed of the optical attenuators. Here is a visual diagram of the ideas presented in the previous slide. Since convolutional operations in the digital domain require at least 2 clock cycles for each sequential multiply accumulate operation, distribution across multiple computing cores is required to alleviate the computational bottleneck. Next are the accelerators. First is the Albiro accelerator. It utilizes Mach-Zehnder modulators and star couplers. This makes an efficient broadcast combined with multicast data distribution. Star couplers are passive devices and consume no power. It leverages parameter sharing thanks to unique wavelength division multiplexing. Leverage shared parameters through passively overlapping receptive fields significantly increases computation parallelism. It utilizes positive and negative currents for positive and negative weights respectively. However, as mentioned previously with electronic circuits, this requires constant power draw to sustain, even though the magnitude of the summed current will be less than either of its components. It is still a constant power drain. Next is the SpaceX chiplet accelerator for deep neural network inference. It proposes a photonic network and data flow co-optimized for deep neural network inference. It enables flexible bandwidth allocation schemes, broadcast-enabled output stationary data flow, and broadcast granularity exploration. This enables one-hop data communication. Furthermore, single chiplet and cross-chiplet broadcast communications. For flexible bandwidth, it is designed to improve network utilization and reduce processing element stalls. This adjusts the communication bandwidth by tuning the number of wavelengths for different types of data. These adjustments are tuned based on the system parameters in the deep neural network layer. For the broadcast-enabled output stationary data flow, it obtains high parallelism and energy efficiency of data communication through the exploitation of the orthogonal broadcast capabilities of the photonic network. This also reduces intermediate data exchange between processing elements thanks to the output stationary nature of the developed data flow. And for the broadcast-enabled output, utilizing broadcast channels can significantly reduce the number of transmitters, which leads to high energy efficiency of data communication. The cost is a moderately higher increase in laser power demand. And here is a side-by-side comparison of the energy breakdown of SpaceX. The majority of the power consumption in both models is the optical to electrical signal conversions, highlighting how costly they can be. It is an area of further research development, but this clearly demonstrates the energy demand, especially in the aggressive model, where 64% of the energy consumed went to the optical to electrical interface. Next is the Sprint chiplet-based accelerator. It is a silicon photonic interconnect for convolutional neural network inference. It leverages the distance independence property of photonic interconnects. Properties such as this and high bandwidth densities allow photonics to overcome the limitations of metallic interconnects. It designs a photonic interchiplet network optimized to adapt to specific communication patterns through utilization of specific convolutional neural network features such as non-uniform bandwidth demand and the recurrence of communication patterns. There is room for significant performance, energy consumption, and scalability improvements for chiplet-based convolutional neural network accelerators. Most prior data flow optimizations in convolutional neural networks sought to reduce the data transmission distance because they were based on electronics and not photonics. This will likely conflict with the distance independence property of the photonic chiplet architecture. And the architecture performs better with weight stationary data flow compared to row stationary data flow. The higher amount of interchiplet communication from streamed pSums out of the accelerator with row stationary data flow increases the latency of sprint compared to weight stationary data flow. Next is the energy consumption breakdown of the Sprint photonic network. Comparing weight stationary to row stationary, a significantly higher portion is taken up by the ring heating, as micro-ring resonators need more adjustments compared to their weight stationary counterparts. And utilizing non-thermal methods could improve this, but utilizing non-thermal methods can improve that. Prior work shortcomings for the previous aforementioned research is that equal bandwidth setup between arbitrary nodes, equal distribution of bandwidth can lead to unnecessarily high implementation costs and energy overhead. Using broadcast opportunities of weights can lead to a loss in broadcast opportunities of input features. Simultaneous broadcast of input features and weights is feasible thanks to the orthogonal scale chiplet and cross-chiplet broadcast capabilities, allowing for broadcast of both weights and input features without sacrifice of either data type. And there are however, there are still limitations of metallic-based interconnects. There are fundamental latency and energy limitations of metallic-based interconnects. Thanks to the properties of photonics such as locality and data communication distance independence, significant energy efficiency improvements of data communication can be made through broadcast opportunities which were not leveraged MEL and metallic interconnects from previous research. Next is a comprehensive study on nanophotonic neural networks. Photonic neuromorphic processors display a reduction of energy consumption. Since photons are self-sustaining, only requiring energy to be generated, there is room for high energy savings in areas such as data transfer. Furthermore, there is no energy consumption other than on the receivers and transmitters. For high operating speeds, since the time of flight of the photon on the scale is near instantaneous, the limitation comes instead from the modulators and other active devices that update between operations. They have effective distribution of computing power, as each neuron simultaneously computes small parts of the larger computational activity, employing the entire system. Furthermore, since photonics generate less heat than electronic circuits, unavoidable issues such as dark silicon can be rectified, where dark silicon refers again to transistors that remain off to meet the thermal power constraint. This study also evaluated and compared different kinds of neural networks. The convolutional neural networks have an advantage over standard neural networks, as the latter can be overloaded with data from their full connection architecture, and it also describes challenges with photonic neural networks, such as for training to take full advantage of photonic technology, it needs specific adaptation to do so. Going back to the evaluate and comparison of different kinds of neural networks, spiking neural networks utilize peak sequences as mechanisms of internal information presentation, incorporating the concept of time in their operating model, which can have better performance and computational cost to traditional neural networks. Speaking of spiking neurosynaptic neural networks, spiking neurosynaptic networks make clever use of phase change materials for weighting. In the amorphous state, the phase change materials represent a strong connection between two neurons because of the high transmission of light. In its crystalline state, it is the opposite, as the majority of the light is absorbed. Phase change material switching only occurs above a certain threshold power. It features adjustable synaptic weights, and due to current fabrication limitations, adjustments are necessary to account for errors within photonic circuits, which can greatly improve the limited yield with current technology. This study also explored supervised and unsupervised learning. Supervised learning is achieved through the use of adjusting the synaptic weights, while unsupervised learning is achieved through the use of predefined update rules, and all artificial neurons need to be recrystallized after each spiking event, which limits operation cycles. Here is a diagram of the neurosynaptic network. Input spikes are passed through a presynaptic input neuron where weights are assigned before being passed to the postsynaptic output neuron, which delivers the output. Referring back to self-training, the method detailed in the source was to use the time of fire as the judge of potentiation or depression of the weights. If an input signal arrives just before a spike was generated, the signal contributed to reaching the firing threshold and therefore was likely excitatory. If a pulse arrives after the spike occurred, it is therefore deemed inhibitory, with the magnitude of this adjustment based on a function of time between the input and output spikes. For the photonic next is the photonic chiplet Taiichi, which was implemented a prototype for this. Distributed optical neural networks have higher robustness than traditional models. Training multiple small neural networks independently has lower cost than training a large traditional model. Going wider can also overcome the limitations of going deeper in physical neural networks, with a lot of developments being made by adding more layers into neural networks. But unfortunately, adding more layers has drawbacks, an example being noise propagation. In deep neural networks, even small errors, when early, have the potential to drastically alter the output. In the case of Taiichi, the extra path from going wider helped correct wrong classification cases. Task and computation distributing can aid in existing photonic integrated circuits and extend their computing capacities. Next is the future endeavors. It may take a considerable period to continuously optimize the architecture or hybrid framework of the optical neural network system to obtain better performances so that they can achieve outstanding results in certain dedicated fields compared to their electronic counterparts. So the first area of research could be fabrication. Fabrication of waveguides and materials are difficult. Every cubic nanometer matters in a waveguide, and current methods of fabrication have bad control in the cubic nanometer scale. In order to cope with variability, there are options to increase the yield due to the excessively tight tolerances. These are enhancing fabrication and construction, variability-conscious circuit design, and programmable and tunable adjustments. One method focusing on the programmable and tunable adjustments. Not only would this alleviate the pressure to fabricate effective devices, it also provides another control surface with which to update the neural network for different applications. Fabrication learning cycles are very costly and slow, as it takes months to fabricate, test, and evaluate. However, creative use of electronic circuit research can aid in expediting the development of photonic neural networks through the use of breakthroughs in certain electronic circuits. Finding a photonic analog may prove beneficial. However, photonics have a different set of constraints. For example, processing near memory solutions in some electronic circuits may not be optimal, as light does not have the same communication drawbacks as electrical circuits. And furthermore, there is a direction of future research could be exploration of implementation technologies. Returning to the point earlier on integrated optical neural networks, further exploration and implementation technologies has high potential to increase optical processor efficiency, as it allows various advantages to be achieved on the same optical neural network. Next are the photonic dot products. There are noise limitations, such as relative intensity noise, shock current, and thermal noise. Relative intensity noise is the normalized optical power fluctuations from the laser sources. This contributes the least to the total noise. Shock current is a discrete event following a Poisson distribution, and the number of discernible optical power amplitudes decreases from variations in the accumulated signals from the noise. Through increasing optical power until relative intensity noise suppresses thermal and shot noise would increase with the precision, which is a method for rectification, which would involve increasing optical power from the lasers. Next is the optoelectronic hybrid structure. All optical cascaded optical neural networks are difficult to achieve. With poor efficiency and nonlinearity, the lack of an all-optical activation function with high nonlinear effect and low loss persists is a key issue that persists over the entire optical network. Under certain conditions, hybrid architectures can perform better than all optical and all electrical designs. Referring back to Pixel, When the number of bits were low and the number of lanes were high, the hybrid design proved greater efficiency than both the all-optical and all-electrical designs. The area footprint for hybrid designs is smaller than that of all optical designs. Employing electronic circuits can reduce the area, as area-intensive functions can be performed electronically. This, however, would incur throughput and power efficiency losses, as electronic circuits have a much lower ceiling than photonics, but it can serve as a viable stepping stone as photonic research continues to make breakthroughs. And furthermore, this hybrid structure can provide a head start, as the electronic side has been heavily researched and developed compared to photonics. Employing electronics can significantly boost the current status of photonic circuits, as previous research can be employed to accelerate the development of photonics. Another area of improvement are storage area, and data flow. Silicon photonics do not have a robust replacement for digital buffering. Optical devices can incur high area compared to electronic counterparts. Inference optical neural networks cannot dramatically expand the number of neurons due to the large footprints of the Mach-Zehnder interferometers or microring resonators of the devices. And photonics favor weight stationary data flows, as writing weights is a time-intensive task. For power and efficiency, conversions from optical to electrical and electrical to optical conversions are costly. Referring back to SpaceX, a large energy penalty is optical to electrical and electrical to optical signal conversion. For the sources presented, their workaround was to simply minimize the amount of signal conversions, but another angle is making signal conversions more efficient. However, to the presenter's knowledge, none of this was explored in any of the sources reviewed. There is poor startup and scalability compared to electronic circuits and hybrid circuits due to signal conversions, area, and other issues. Most optical improvements struggle to beat electronic circuits in small-scale limited applications, such as Pixel's all-optical network in the 1-bit per lane situation, in part due to costly signal conversions as mentioned above. And furthermore, research can be done in the feasibility of optical stochastic computing. Stochastic computing has potential in the optical domain and was only explored in one source. To the presenter's knowledge, there are not many sources on the stochastic computing, and while in its infancy, it still has great potential. This concludes the presentation for the EE503 final survey project assignment. The sources used will be linked in the description. Thank you for your time.